gravity begins quietly. It is not a shout from the heavens or a flash of light, but a whisper that holds everything together. On Earth, it is the reason oceans rest within their basins, instead of drifting into the airless dark. It keeps mountains grounded, rivers flowing downhill, and the breath within our chests tethered to this planet. Every step we take, every leap, every falling leaf is a small conversation with gravity, the silent sculptor that defines our world. When we drop a stone, it falls not because it chooses to, but because the fabric of reality curves gently toward the heart of the Earth. That same curve holds the moon in its graceful orbit, its motion locked in an endless dance that lifts and lowers tides across every shore. Gravity anchors the rhythm of the oceans, the tilt of continents, the pull of our blood, and the slow spin of the planet itself. If one could rise beyond the clouds and drift above the blue sphere, the pattern continues. Gravity keeps Earth circling the sun, just as the moon circles Earth. The pull that holds us down also binds our world to its parent star, creating a cosmic balance that has endured for billions of years. And beyond that, in every direction, the same invisible law repeats itself. Planets orbit stars, stars gather into galaxies, galaxies swirl into clusters and filaments that span the observable universe. At first glance, gravity seems like a force that pulls, an unseen hand that drags matter toward matter. That is how Isaac Newton saw it, describing a universe where every object attracts every other object in direct proportion to its mass and inverse proportion to the square of its distance. His formula explained the motion of the planets, the fall of an apple, and the tides of the sea with astonishing precision. For centuries, the Newtonian view ruled unchallenged. Yet even Newton admitted he did not know how this invisible action occurred across the void. What exactly was pulling, and why did it never fail? Centuries later, Albert Einstein changed everything. He looked at gravity not as a force, but as the shape of space-time itself. In his theory of general relativity, mass and energy tell space-time how to curve, and space-time tells matter how to move. A planet or a star does not feel a pull in the traditional sense. It follows the curvature of the space-time it occupies. Imagine a great sheet stretched tight, and upon it rests a heavy sphere. The fabric bends beneath it. If a smaller object rolls nearby, it moves along that curve, not because it is being tugged, but because straight lines no longer exist there. This vision of the cosmos is both beautiful and humbling. Gravity is not something acting on space and time, it is space and time. Every massive thing, from a pebble to a black hole, reshapes the geometry of the universe. When light passes near a star, its path bends, not because light can be grabbed, but because the space it travels through is warped. When a clock ticks near a massive planet, time itself slows, stretched by the same curvature. Einstein's insight revealed that gravity and time are inseparable, partners in a cosmic waltz that choreographs every motion we observe. And yet, for all its familiarity, gravity remains mysterious. It is the weakest of the four fundamental interactions. A small magnet can lift a paperclip against the entire gravitational pull of the Earth. That comparison alone seems absurd, and yet it tells us something profound. Gravity is weak, but it never cancels out. While positive and negative electric charges neutralize each other, there is no negative mass to oppose the positive. Every atom in the universe contributes its pull to every other atom. That persistence is why gravity, though weak, dominates the grand structure of the cosmos. From the collapse of stars to the birth of galaxies, from the fall of raindrops to the steady orbits of moons, gravity governs all that moves and all that stays still. It is the quiet architect of order, the sculptor of everything from mountains to space-time itself. But its true nature raises an even deeper question. If gravity is a property of space-time curvature, then it depends on the geometry and energy distribution of our universe. But what if another universe existed, one with different geometry, different energy, or even different laws of physics altogether? Would gravity there behave the same way? Would it curve space and time as it does here? Could there be universes where gravity repels instead of attracts, or where it fades into something else entirely? Such questions are not fantasy. They arise naturally from the mathematics of relativity, from the quantum theories that challenge it, and from cosmological models that suggest our universe might not be the only one. The multiverse hypothesis, though still debated, forces us to confront the possibility that gravity as we know it is only one version of a deeper principle, a pattern that could vary or vanish elsewhere. To even begin to answer this, we must first understand how gravity truly works in our own universe. We must peel back the layers of Einstein's theory, explore the curvature of spacetime, and confront the places where our understanding fails, at singularities, in quantum scales, and at the edge of the cosmic horizon. Only then can we ask whether gravity, the force that shapes everything we know, might take on new forms in other realms of existence. The story of gravity is the story of structure, of time, of everything that stands against chaos. It is the story of how the universe learned to hold itself together. And as we trace that story, from falling apples to colliding galaxies, we move closer to the ultimate question. Is gravity universal or merely local to the universe we inhabit? The answer lies in the curved fabric beneath our feet and the endless sky above our heads. To find it, we must look beyond Newton's pull and Einstein's curvature, into the deeper mechanisms that may connect gravity to information, quantum entanglement, and even the origin of space itself. For now, we begin where we stand, held fast by the gentle pull that makes life possible and prepares us to journey outward into the mystery of the cosmos. Gravity defines the stage upon which everything unfolds. It is the quiet director behind the grand performance of existence. Every motion, from the smallest drifting particle to the slow rotation of galaxies, is a trace left upon the curved geometry of space-time. Though invisible, it writes the laws that guide suns and planets, and it whispers through the smallest grains of dust suspended in the air. Imagine standing on the surface of Earth and feeling that constant downward pull. We think of it as a force that drags us toward the planet's center, but Einstein's vision tells a different story. What we feel is the natural motion of objects following the curvature of space-time, like leaves floating along a slow-moving stream. Our bodies are trying to follow the straightest possible path through space-time, yet the solid ground beneath us resists. The sensation of weight is not a pull downward, but the push upward of the Earth itself, refusing to let us fall along the curve we are meant to follow. Now imagine removing all matter from the universe. No planets, no stars, not even a single atom. What remains is flat space-time, a perfectly still stage where no curvature exists. In such emptiness, an object set in motion would glide endlessly in a straight line, forever unaware of direction or destination. Only when mass or energy enters does the geometry twist and paths bend. This bending is not just a mathematical trick, it is the physical shape of reality. Space curves, time stretches, together they weave the flow of cause and effect. The proof of this idea arrived not through imagination, but through experiment. When light from a distant star passed near the sun during an eclipse in 1919, astronomers measured its deflection exactly as Einstein's equations predicted. That moment changed science forever. It proved that even light, which has no mass, follows the curvature created by massive bodies. Later, other tests confirmed the theory again and again. The precession of Mercury's orbit, the slowing of time in strong gravitational fields, and the detection of gravitational waves by LIGO a century later all point to the same truth. Gravity is geometry. Yet this elegant picture hides an unsettling truth. Einstein's equations describe gravity perfectly on large scales, but when we attempt to apply them to the smallest realms of reality, they break apart. Quantum mechanics, which governs atoms and particles, refuses to bend easily into the same fabric. The equations of general relativity tell us how mass and energy shape spacetime, but quantum theory tells us that energy fluctuates even in the vacuum, that particles pop in and out of existence in a sea of uncertainty. When we try to merge the two, infinities arise, as if the mathematics itself protests the union. This tension between the smooth curves of relativity and the jittering probabilities of quantum theory is the central problem of modern physics. We can describe the universe from galaxies down to molecules, but not to the scale of the Planck length, that unimaginably small realm where space and time might cease to be continuous. There, gravity may not be a curvature at all, but something emergent, a byproduct of deeper quantum interactions. For now, our universe appears consistent, obeying the same gravitational laws everywhere we look. The motion of galaxies billions of light years away follows the same equations that keep the moon in orbit. But if the constants that define gravity were even slightly different, everything we see could vanish or transform. The gravitational constant, often written as g, sets the strength of the curvature caused by mass and energy. If g were stronger, stars would collapse faster, their lives ending in violent bursts of radiation. If g were weaker, clouds of gas might never form stars at all. This delicate balance makes our cosmos possible. Stars live long enough to forge heavy elements, planets form within their orbits, and life arises in the narrow calm between chaos and collapse. It is a balance so precise that even a tiny deviation would create an entirely different universe. But is that balance inevitable, or is it an accident of our particular reality? The more we study the universe, the more it seems that many of its features are finely tuned for stability. The ratio between electromagnetic and gravitational forces, the speed of light, the density of dark energy, all exist within narrow ranges that permit stars, chemistry, and life. Change one, and the entire system collapses or freezes. Such precision invites the question of why. Why should gravity be just strong enough to bind galaxies, yet weak enough to let the universe expand? Why should the constants that govern its behavior produce complexity rather than chaos? Some scientists suggest that we notice this balance simply because we are here to notice it. This is the essence of the anthropic principle. If the universe had been different, no observers would have existed to question it. Yet that explanation, while logically sound, feels incomplete. It answers the question of why us by avoiding the question of why gravity at all. To search for that answer, we must consider something even more audacious: the possibility that our universe is not unique. That beyond the reach of our telescopes, beyond the observable horizon, countless other universes exist, each with their own constants, their own versions of gravity, their own rules for the dance between space, time, and matter. In some, gravity could be stronger, tearing worlds apart before life begins. In others, it could be weaker, leaving a void too empty for light to gather. The idea may seem speculative, but it arises naturally from cosmology itself. When we trace our universe back to its first moments, to the era of inflation, we find that tiny fluctuations in quantum fields could have created isolated regions of space that inflated separately, forming bubbles of reality disconnected from ours. Each bubble could possess its own values for the constants of nature. In that landscape of possibilities, our universe is only one note in a cosmic symphony of many keys. If that is true, then gravity, as we know it, is not the universal law we imagine, but a local expression of a deeper framework, a kind of regional dialect in the language of physics. To understand how gravity might differ in those other realms, we must first grasp every contour of how it operates here. Einstein gave us the map, but quantum theory reminds us that the map may not show every layer of the terrain. Somewhere beneath the smooth fabric of space-time lies a deeper pattern, and whatever that pattern is, it could change completely in another universe. If one could drift beyond the visible stars, leaving behind the glow of galaxies and the echo of their clustered gravity, there might come a place where even space itself begins to thin. Out there, the familiar structure of space-time could fade into something simpler or stranger, a reminder that the rules we take as absolute may only belong to this universe. To imagine another realm is not to abandon science, but to follow its logic to its furthest horizon. Gravity, though deeply tested here, may not always take the same form. In our cosmos, its presence is inseparable from the geometry of space-time. Einstein's equations link mass, energy, and curvature in a way that allows prediction and precision. From the bending of light around distant clusters to the slow drift of satellites around Earth, every test so far has confirmed that relationship. Yet each confirmation also deepens the mystery, because gravity behaves as though it is continuous and infinite, while everything else in nature, from light to matter, obeys quantum rules. At the smallest scales, quantum mechanics describes a universe built from probabilities, where particles are excitations of underlying fields. If space and time themselves are fields, then gravity should have a quantum description too. Physicists have searched for it for decades, through string theory, loop quantum gravity, and other ideas that attempt to unite Einstein's smooth geometry with quantum uncertainty. None has yet succeeded completely, but each offers hints that the space-time we know may be only an approximation, a large-scale illusion built from something more fundamental. String theory proposes that everything, including the graviton, the hypothetical particle that would carry the gravitational interaction, arises from tiny, vibrating strings. These strings can exist only in higher dimensions beyond the four we experience. In those extra dimensions, gravity might spread out or leak, explaining why it appears so weak in our universe. Loop quantum gravity takes a different route, suggesting that space-time itself is made of discrete loops, woven together like a cosmic fabric. In both visions, gravity is not continuous, but granular, emerging from microscopic geometry. If one of those theories is correct, then our version of gravity is not inevitable. In another universe with different dimensions or a different quantum structure, gravity could behave entirely differently. It might not follow an inverse square relationship. It might not even attract. It could confine or oscillate or vanish in certain regions, leaving pockets of space-time untouched by curvature. In such a universe, motion itself would lose meaning, and the concept of orbit or mass might never arise. The implication is profound. Gravity may not be a universal law, but a local phenomenon, one expression of a broader mathematical landscape. Our cosmos happens to occupy a region of that landscape, where geometry curves in a way that allows stars, planets, and life to exist. But elsewhere, the equations could resolve differently, forming worlds where the very notion of structure is alien. When we speak of other universes, it is easy to imagine them as distant bubbles floating in some vast space. Yet space itself is part of what changes. Each universe could have its own metric, its own version of distance and time. Gravity would not merely be weaker or stronger, it could redefine what distance and time even mean. In one universe, a second might stretch longer than an hour here. In another, space could fold upon itself in closed loops, where gravity traps not objects, but the geometry itself. And still, even within our own cosmos, gravity holds surprises. The discovery of dark energy revealed that the universe's expansion is accelerating, as though gravity, on the largest scales, has turned from attraction to gentle repulsion. The cause remains unknown. It could be a cosmological constant, a property of space-time, or it could be the hint of a fifth force, something that modifies gravity at cosmic distances. If such modification exists here, imagine what it might mean elsewhere, in realms where that effect dominates completely. Perhaps in some universes, gravity never formed bound structures, leaving only diffuse fields of light. In others, it might have crushed matter into eternal density, filling the cosmos with endless horizons. And somewhere between those extremes, our universe found a balance, allowing complexity to bloom in the narrow window between collapse and dispersal. The beauty of this balance is not just mathematical, but existential. Without gravity's gentle precision, there would be no stars to forge elements, no planets to cradle oceans, no minds to wonder why. The same force that pulls an apple to the ground also holds galaxies together across billions of light years. It is both intimate and cosmic, both familiar and unfathomable. If there are other universes, their versions of gravity may tell different stories, yet all of them, in their own ways, would sculpt the possibilities of matter and time. Whether strong or weak, attractive or repulsive, gravity defines what can exist. It is not just a law, but the shape of destiny for every universe it governs. In our world, it binds atoms into bodies, bodies into worlds, and worlds into systems that orbit in quiet harmony. It bends light and slows time, weaving every event into the tapestry of causality. To imagine a cosmos without it is to imagine existence without connection, motion without meaning, time without memory. So we return to the question that began this journey. Would gravity work the same in another universe? Perhaps not. Yet the deeper truth may be that gravity, whatever its form, is always the expression of order within chaos, the way reality holds itself together against the infinite. Whether as curvature, entanglement, or emergent pattern, it remains the signature of something profound, the rhythm of existence itself. And so, as we stand beneath our familiar sky, held gently to the earth by a pull we barely feel, yet could not live without, we are reminded that gravity is more than a force. It is the silent agreement between space, time, and matter that makes everything possible. It is the foundation upon which all universes, known and unknown, may rise or fall. Imagine standing at the edge of a quiet lake on a calm night. A single pebble dropped into the water sends ripples across the surface, each wave spreading outward in perfect circles. Now replace the water with the fabric of space-time and the pebble with a star. That is how gravity reveals itself, not through invisible threads pulling across empty space, but through the warping of the very arena in which motion occurs. Every planet, every star, every galaxy leaves its own subtle imprint upon this cosmic lake, shaping the flow of everything around it. Einstein's general theory of relativity, first presented in 1915, turned the universe inside out. It told us that gravity is not a force transmitted between objects, but a result of geometry. Space and time are woven together into a single continuum, and this continuum bends wherever energy and mass exist. Objects move along the straightest possible paths within this curved geometry, paths known as geodesics. To an observer, those paths appear as attraction, but the reality is simpler and deeper. Nothing is pulling anything. Everything is simply following the shape of reality itself. If one could see space-time, it would not be flat and empty. Around Earth, it would appear as a gentle depression, deeper near the core, shallower near the sky. Around the Sun, the depression would stretch far into the solar system, guiding the planets in their orbits like marbles rolling around a great invisible bowl. Even light, which has no mass, bends as it passes near this curve. The images of distant galaxies stretched and mirrored across the sky, a phenomenon known as gravitational lensing, are direct evidence of this bending. But space-time is not just a stage. It is active, dynamic, alive with the motion of energy. When massive objects accelerate, they send ripples through space-time, gravitational waves that travel at the speed of light. These waves were first detected a century after Einstein predicted them, when the LIGO Observatory measured the faint trembling of space-time caused by the collision of two black holes. That discovery confirmed that gravity is not a static field, but a living vibration of the universe itself. To feel gravity is to live within geometry. A person standing on the surface of Earth is constantly being pushed upward by the ground. resisting the natural path through curved spacetime that would otherwise lead toward the planet's center. In orbit, astronauts feel weightless, not because gravity disappears, but because they are falling freely along that curved path, following it perfectly. The International Space Station, for instance, is not beyond Earth's pull. It is immersed in it, continuously falling, yet never hitting the surface because the planet curves away beneath it. The connection between gravity and time is one of Einstein's most remarkable insights. Clocks run slower in stronger gravitational fields. Time passes a little more slowly at sea level than at the top of a mountain, though the difference is too small for human senses to notice. Near a black hole, however, the effect becomes dramatic. To an observer far away, time near the event horizon appears almost frozen, as if the universe itself pauses at the edge of infinite curvature. This relationship means that gravity does not just shape space, it sculpts time as well. Every test of general relativity so far has supported Einstein's vision. The orbit of Mercury, once an unsolved mystery under Newton's equations, fits perfectly within Einstein's curved spacetime. The bending of light from distant quasars, the precise timing of pulsars in binary systems, and the image of the shadow of a black hole captured by the Event Horizon Telescope all affirm that spacetime curvature is real. Even the expansion of the universe, discovered by Edwin Hubble, can be described within the same framework, as the stretching of spacetime itself, rather than the motion of galaxies through a pre-existing void. Yet despite its success, general relativity leaves questions unanswered. It does not explain what happens inside singularities, where curvature becomes infinite, and known physics collapses. It cannot describe the gravitational behavior of the universe at the smallest scales, where quantum effects dominate. And it offers no account of why gravity is so much weaker than the other forces, why it takes the entire Earth to make us feel its pull, while a tiny magnet can lift a piece of metal against it. The search for answers has driven physicists toward the boundaries of both relativity and quantum theory. If spacetime curves, perhaps it also fluctuates, foaming and bubbling at the Planck scale, where distances are so small that even geometry may not be continuous. Some researchers believe that spacetime itself emerges from a deeper quantum structure, one built from entanglement and information rather than points and coordinates. In that case, gravity would not be a fundamental interaction at all, but a byproduct of something else entirely, a statistical effect, like pressure or temperature, arising from countless microscopic processes. These ideas, though still developing, hint at a profound possibility. Gravity, the most familiar and ancient force in our understanding, may not be a force at all, but an emergent property of the universe's underlying information network. If that is true, then in another universe where that network follows different rules, gravity could take on entirely different behavior. It might not bend space, but twist time. It might not propagate as waves, but as changes in probability. The geometry we take for granted could be only one version among countless possibilities. Our universe, as elegant as it is, might be one particular solution among many. The constants that define the strength of gravity, the speed of light, and the curvature of space-time could differ elsewhere. What we call a gravitational constant might be only a local calibration, the result of our specific cosmic configuration. Even the number of dimensions could vary, altering how curvature behaves. To grasp this possibility, one must see gravity not as an unchanging law, but as a relationship between matter, energy, and the fabric of existence itself. Change one element, and the relationship transforms. In another universe, mass could create different kinds of curvature, or energy might not curve space at all. There could be realms where geometry itself is unstable, or where space-time is not even a continuous field, but a discrete network that reconfigures as events unfold. Gravity, then, may not be universal. It may be contextual, a phenomenon that depends entirely on the structure of the cosmos that contains it. This is why Einstein's theory, though magnificent, may only describe a single chapter in a larger story. To read the rest, we must explore beyond the boundaries of our own space-time, into the possibilities suggested by quantum gravity, by multidimensional models, and by the idea that the universe itself is one of many. As we move deeper into this question, we will find that the behavior of gravity depends not only on equations but on the constants that define the scale of everything. Those constants may not be fixed in every universe. The next step in understanding how gravity could differ elsewhere is to examine those numbers: the gravitational constant, the speed of light, the Planck constant, and see how delicately they are balanced in our own reality. Only then can we imagine how gravity might behave when that balance changes. Gravity's nature is not confined to mathematics alone. It is revealed in how the universe behaves when nothing resists its logic. When a star dies, gravity takes command, pulling its matter inward until the collapse creates something so dense that not even light can escape. The result is a black hole, a region where space-time curves so sharply that every possible path points inward. For an outside observer, it is an object of infinite patience, swallowing light and time with equal hunger. For the laws of physics, it is a place of surrender, where the equations of general relativity and quantum theory meet and fail to agree. Within that failure lies the key to understanding why gravity might behave differently elsewhere. The singularity at a black hole's center is not a physical point, but a signal that our mathematics has reached its limit. The curvature becomes infinite, and time itself ceases to have meaning. To describe what truly happens there, we would need a theory that unites the geometry of Einstein with the quantum uncertainty of the subatomic world. Without that union, gravity remains only half understood. Physicists have long searched for a bridge between these two great theories. Quantum field theory describes all the other forces through exchange particles: photons for electromagnetism, gluons for the strong nuclear force, and W and Z bosons for the weak nuclear force. If gravity fits the same pattern, it should have a carrier particle too, called the graviton. The graviton, if it exists, would be massless and move at the speed of light. Yet no experiment has ever detected it. Its effects are too small, too subtle, hidden beneath the vast smoothness of space-time. Some theories suggest that we will never find gravitons because gravity is not fundamental. It could be emergent, arising from the collective behavior of microscopic degrees of freedom. Just as temperature arises from the motion of molecules, gravity might arise from the information contained within space-time itself. This is not philosophy but mathematics, hinted at by the deep connections between gravity, entropy, and information theory. When matter falls into a black hole, its information seems lost, but quantum theory insists that information cannot disappear. The tension between those truths may reveal gravity's true nature. Other models, like string theory, propose that everything, including space-time and gravity, is made from vibrating one-dimensional strings. Each vibration corresponds to a particle, and the way those strings move depends on the geometry of higher dimensions. In that framework, gravity could be a side effect of how strings stretch and twist across those unseen directions. Our universe might exist on a four-dimensional surface called a brane, floating within a higher dimensional space known as the bulk. Gravity, being the only interaction that can travel through the bulk, would appear weaker than the others because it spreads through more dimensions. If such a vision is true, then there could be other branes nearby, parallel universes with their own forms of gravity. Their presence could subtly influence ours, like faint echoes in the curvature of space-time. Perhaps what we call dark matter, the invisible mass that binds galaxies together, is not matter at all, but gravity leaking from a neighboring universe. Though speculative, these ideas are consistent with Einstein's equations extended into higher dimensions. Every time physicists test gravity, the results return the same message. General relativity works perfectly, but only up to a point. It describes the motion of planets, the bending of light, the expansion of the universe, and the merging of black holes. But at the smallest scales and the highest energies, its certainty dissolves. The universe becomes pixelated, time and space fluctuate, and gravity begins to lose its familiar shape. To imagine how gravity might differ in another universe, one must imagine a cosmos where those limits shift. Suppose the quantum scale were larger, or the gravitational constant stronger. The curvature of space-time would become more dramatic, and the boundary between classical and quantum worlds would blur. Particles might collapse into black holes almost instantly, or space might tear itself apart under its own weight. Conversely, if gravity were weaker or space-time smoother, quantum effects could dominate even at large scales, producing a universe that never coalesces into stars or planets. The geometry of the universe determines the nature of gravity, but gravity also determines the geometry of the universe. They form a feedback loop, a self-consistent structure in which the shape of reality defines the rules of motion, and the rules of motion define the shape of reality. Change the constants that govern that loop, and everything changes with them. The formation of matter, the passage of time, and the meaning of existence itself. Every scientific test we perform, from the timing of pulsars to the detection of gravitational waves, reminds us that our understanding of gravity is both precise and incomplete. It works perfectly for the universe we inhabit, yet it may be only one version of a deeper truth. Other universes could operate on different geometries, with constants that shift the balance between curvature and energy. In those realms, gravity might not look anything like the gentle pull that keeps us bound to Earth. It could be fierce, fleeting, or altogether absent. Still, within our cosmos, the curvature model holds strong. It explains the arcs of starlight, the warping of time, and the expanding web of galaxies stretching across billions of light years. Gravity, as Einstein described it, is the universe's handwriting, a continuous record of every mass and every motion. It shapes not just where things move, but when they exist. The future of every particle is written upon that curved fabric, and so is our own. As we continue to probe deeper into the nature of space-time, we move closer to understanding how fragile and specific our version of gravity truly is. It depends on constants that seem arbitrary yet precise, numbers that define how reality balances itself between collapse and chaos. The next step in unraveling gravity's mystery is to study those constants, to see how a universe finely tuned for balance could arise from infinite possibilities. Gravity is the great negotiator of existence. Every atom, every burst of light, every drifting cloud of gas follows its silent rule. Yet its precision depends entirely on numbers so small and specific that a slight change would remake the universe from the ground up. The gravitational constant, the speed of light, and the Planck constant together define the stage upon which reality performs. They are the hidden ratios that decide whether stars can shine or whether matter can even exist. In our universe, these constants align perfectly to permit structure. The gravitational constant, often represented as g, determines how strongly mass curves space-time. Its measured value is small, which is why gravity is weak compared to the other forces. If g were even slightly larger, stars would burn through their fuel in moments, collapsing under their own weight into black holes. If it were smaller, the diffuse gas of the early universe would never have condensed into the first stars at all. There is only a narrow window in which balance is possible, and our cosmos exists precisely within it. The speed of light, written as c, also defines how gravity behaves. It determines how fast changes in curvature can propagate through space-time. When a massive body moves or collapses, the distortion in space-time travels outward at that exact speed, creating gravitational waves. If the speed of light were different, those waves would carry information differently, and the balance between space and time would shift. In some hypothetical universes, where light might travel faster or slower, gravity could act instantaneously or sluggishly, erasing the harmony between cause and effect. Then there is the Planck constant, symbolized as h-bar, which sets the scale of quantum effects. It determines how energy and frequency relate, and therefore how particles behave at the smallest levels. Combine g, c, and h-bar, and one can construct quantities like the Planck length and Planck time, the smallest meaningful measurements of space and time. At those scales, gravity and quantum mechanics must intertwine. Change any of these constants, and the structure of spacetime itself changes, perhaps breaking the connection between geometry and motion entirely. This delicate calibration has led many scientists to wonder why the numbers are as they are. The anthropic principle offers one answer. We observe a universe that allows life simply because life cannot exist in universes that do not allow observation. But that answer feels circular, as if the cosmos tailored itself to our curiosity. Still, it captures a profound truth. Gravity must be almost exactly what it is for complexity to emerge. Cosmologists such as Paul Davies and Max Tegmark have explored this fine-tuning deeply. Tegmark's mathematical universe hypothesis suggests that every possible set of constants corresponds to a different universe, each as real as ours. Most of these universes would be barren, their gravitational behavior leading either to instant collapse or eternal expansion. Ours is one of the rare few where gravity balances perfectly with the other forces, allowing stars to form, elements to combine, and minds to arise that can wonder about the balance itself. This fine-tuning is not merely philosophical, it has measurable consequences. When astrophysicists simulate universes with different constants, they find that gravity dominates the outcome. Increase G slightly, and stars collapse before fusion can stabilize them. Decrease it slightly, and no stars ignite at all. In between lies a razor-thin corridor of stability where long-lived stars, complex chemistry, and habitable worlds can exist. Our universe walks that corridor as if by accident, yet the precision is astonishing. The formation of galaxies also depends on that balance. Gravity gathers matter, but radiation pressure and expansion push it apart. If gravity were weaker, the expanding universe would have outpaced the formation of structure, leaving only a thin haze of hydrogen. If stronger, the cosmos would have collapsed into black holes long before planets formed. The vast filaments of galaxies that span billions of light years exist only because gravity found a perfect compromise between creation and destruction. Such balance is not static. Over cosmic time, the interplay between gravity and dark energy decides the universe's fate. If dark energy continues to accelerate expansion, galaxies will drift apart faster than gravity can pull them together, and the night sky will eventually fade into darkness. But if gravity somehow grows stronger in the future, perhaps through changes in its coupling to matter, the universe could reverse its expansion, collapsing in a final convergence known as the Big Crunch. In either outcome, gravity remains the arbiter of cosmic destiny. The more precisely we measure it, the more fragile it seems. Laboratory experiments have tested gravity's strength down to the millimeter scale, searching for deviations that might hint at hidden dimensions or new forces. So far, the results match Einstein's predictions perfectly. Yet cosmological observations, especially those involving dark matter and dark energy, suggest that our understanding of gravity may still be incomplete. It behaves one way in galaxies and another way on the cosmic scale, hinting that there might be layers to its nature we have yet to uncover. Perhaps gravity is not a single phenomenon, but a spectrum of effects, each emerging from deeper principles. In that case, our constants, G, C, and H bar, could be local values, specific to this universe's configuration of fields and energies. In another universe, those values could shift, changing everything from the curvature of space to the passage of time. The very concept of attraction might lose meaning, replaced by interactions we cannot yet imagine. Our universe, balanced between infinite possibility and fragile precision, seems to exist on a knife's edge. Gravity, the weakest of all forces, has turned out to be the most decisive. It organizes chaos, defines the shape of time, and gives permanence to matter. Its constant, G, is both small and mighty, a whisper that holds galaxies together. And behind that whisper lies a question so large it can barely be spoken. Is this balance an accident, or the inevitable result of some deeper order shared across all universes? To explore that question, we must step beyond the confines of our own cosmos and consider the idea that there might be many universes, each born from its own burst of inflation, each with its own set of constants, each with its own version of gravity. The next chapter follows that idea to its source, tracing the theory of cosmic inflation and the birth of the multiverse. There, among infinite possibilities, we may find the first clues to how gravity could behave in worlds beyond our own. When we look into the night sky, we see a universe that feels inevitable. Stars burn, galaxies spin, planets circle their suns, and life exists to witness it all. Yet none of this was guaranteed. The balance that makes it possible is so fragile that even the smallest change in the laws of nature could erase everything we know. Gravity, the gentle sculptor of the cosmos, is only one part of that balance, but it is the part upon which all others depend. The strength of gravity determines the architecture of existence. A universe where gravity is just a little stronger would be a place of constant collapse, filled with short-lived stars that burn violently before imploding into black holes. A universe where gravity is weaker would be cold and barren, its gas clouds too diffuse to form stars at all. The value of the gravitational constant seems tuned to an almost impossible precision, allowing just enough attraction for complexity to emerge without surrendering to chaos. This notion of fine-tuning extends beyond gravity. The speed of light defines how energy and information move through spacetime. The charge of the electron determines the strength of electromagnetic interactions. The mass of the proton sets the scale of atomic stability. Change any of these by even a fraction, and the universe would look nothing like ours. At first, this may sound coincidental, but the numbers are so exact that coincidence begins to feel like an insufficient word. Consider the gravitational constant, G, again. Its value decides how quickly matter collapses into structures. If G were increased by only a few parts in 1,000, the first stars would have formed too quickly, fusing their hydrogen in brief flashes rather than the steady glow that sustains life-bearing planets. If decreased, the early universe would have expanded too rapidly for galaxies to form. The precision needed is staggering, as though the universe itself were balancing on the edge of a cosmic blade. Then there is the cosmological constant, the term in Einstein's equations that represents the energy density of empty space. For decades, Einstein thought it unnecessary, calling it his greatest mistake. Yet in the late 20th century, astronomers discovered that the universe's expansion is accelerating, a sign that some form of dark energy, akin to the cosmological constant, is real. The measured value of that energy is extraordinarily small, but not zero. If it were slightly larger, the universe would have expanded so rapidly that matter could never clump together. If smaller, it would have collapsed long ago. Again, the tuning appears impossibly precise. Such coincidences have led scientists and philosophers to propose the anthropic principle, the idea that the universe must have properties that allow observers like us to exist, because otherwise we would not be here to notice them. It is not a mystical argument, but a logical one. We find ourselves in a universe where gravity and all other constants permit life simply because universes that do not permit life contain no one to ask the question. The anthropic principle can sound circular, yet it captures a deep truth about observation itself. Every measurement we make is filtered through the fact of our existence. Still, some find it unsatisfying, seeing it as a label for our ignorance rather than an explanation. Why should the constants take these particular values at all? Are they truly fundamental, or could they vary in other realms of reality? Cosmologists like Paul Davies have suggested that perhaps the laws of nature are not fixed, but shaped by the universe's history. In this view, Constants such as g might not be absolute numbers, but results of cosmic evolution. Others, like Max Tegmark, take the idea further, proposing that all possible sets of constants exist somewhere in a vast multiverse, each defining a different universe with its own physical laws. Our universe, then, would be one among countless others, not special except in the sense that it supports consciousness. The evidence for such ideas is indirect but compelling. The theory of cosmic inflation, which describes the universe's rapid expansion in its earliest moments, naturally predicts the creation of many separate regions of space-time, bubbles that could have cooled differently, each with its own values of physical constants. In that picture, our universe is not the only outcome of the Big Bang, but one of many, each governed by its own version of gravity. If that is true, then fine-tuning is not a miracle, but a selection effect. Out of all possible universes, we inhabit the one where gravity happens to allow stability and life. The question then shifts from why these numbers to how many versions exist. The constants of nature may vary across the cosmic landscape, and gravity, the quiet sculptor of form, might bend and behave in ways we can scarcely imagine elsewhere. Even within our own cosmos, we see hints that gravity's behavior is not entirely uniform. The motions of galaxies imply the presence of unseen mass, dark matter, that amplifies gravitational effects without emitting light. The accelerating expansion of space suggests another hidden component, dark energy, acting in opposition to gravity. These mysteries remind us that even here, gravity's full story is not yet told. Perhaps its apparent weakness or its long reach are not intrinsic properties, but emergent consequences of deeper laws we have yet to uncover. The fine-tuned harmony of constants is not just a curiosity, it is the reason anything exists. The mass of the electron, the strength of gravity, the ratio of matter to radiation, all combine to create a universe that endures long enough for stars to live and die, for carbon to form, for beings to think. Change the tuning, and the melody collapses. To imagine gravity working differently is to imagine the music of the cosmos in another key. There could be universes where stars flicker and vanish before planets cool, or where no gravity at all exists to bind matter into form. Yet there could also be universes where entirely new patterns arise, governed by forces we have not yet conceived. The possibilities are endless, but they all depend on the same question: how stable is the architecture of reality itself? As we explore that question, we find ourselves at the edge of speculation and observation. We can measure the constants of our universe with exquisite precision, but we cannot yet say whether they are unique or merely local. To look for answers, we must step beyond our own cosmic bubble and consider the next idea, the possibility that our universe is one of many, each born with its own laws, its own geometry, and its own gravity. If the universe were a single note, it would hum in a pitch determined by its constants. The gravitational constant, the speed of light, the Planck constant, the strength of the nuclear forces, together they compose the cosmic symphony that defines existence. The precision of these numbers is so exact that it defies casual explanation. If they were inked even slightly differently, the stars above would not burn, the planets would not orbit, and the chemistry of life would not awaken. Gravity's role in this orchestra is that of the conductor, subtle yet absolute, keeping time for the rest. When scientists calculate how small a change would erase this balance, the numbers become almost impossible to grasp. If the gravitational constant were altered by 1 part in 10 to the power of 60, the universe would become unrecognizable. That ratio is so extreme that it makes the width of a human hair compared to the size of the observable universe seem enormous. Such precision is either a coincidence so rare it strains belief, or it hints at something deeper, a principle that shapes universes to be stable, even if most remain barren. One way to think of this is through the lens of the anthropic principle again, not as a statement about human importance, but as a rule of selection. Out of countless universes, only those with the right balance between gravity and expansion produce long-lived stars. Within those stars, heavy elements are forged and scattered, allowing chemistry to begin. The very act of noticing this balance becomes evidence of its necessity. We are not lucky observers of chance. We are the inevitable consequence of cosmic parameters that allow observation at all. Yet the anthropic view is not the only explanation. Some physicists, such as Lee Smolin, have proposed that universes might reproduce in a way analogous to biological evolution. In Smolin's model of cosmological natural selection, each black hole could give birth to a new universe inside its singularity, with slightly varied physical constants. Universes that produce many black holes would therefore generate more offspring, leading over cosmic generations to a population of universes fine-tuned for stability and star formation. In that framework, gravity strength would evolve toward values that maximize black hole production, which by coincidence also favor long-lived stars and complex chemistry. It is a daring idea, unproven yet profoundly logical. It suggests that our universe might not have been designed or randomly chosen, but shaped by a kind of cosmic Darwinism. If true, the laws we experience are the result of survival among universes, gravity fine-tuned not for life directly, but for persistence. Life would then be an incidental but inevitable outcome, flourishing in the rare environments where stability endures. There are other possibilities. Some researchers propose that what we call constants might not be fixed at all, but could vary slowly over cosmic time. Observations of distant quasars have hinted, though not conclusively, that the fine structure constant may have been slightly different billions of years ago. If so, the strength of gravity might also evolve subtly as the universe expands. That would mean the cosmos itself is not frozen, but still adjusting, still finding equilibrium as it ages. The fine-tuning problem also invites questions about mathematics itself. Max Tegmark argues that every consistent mathematical structure exists as a physical reality. In that mathematical universe view, all possible configurations of constants are realized somewhere. The set of universes where gravity behaves differently is infinite, and we inhabit the one whose structure allows consciousness to recognize it. If true, then there is no mystery of tuning, only selection, the vast space of all possible realities, each governed by its own numbers, its own geometry, its own gravity. In these ideas, gravity's value becomes a kind of address, identifying our universe in the endless landscape of possible laws. The number that defines G is not arbitrary. It is the coordinate that determines how matter curves space and how space responds. It sets the scale of stars, the lifetime of galaxies, and the rhythm of time itself. A small shift in that coordinate, and the entire architecture of reality would transform. Such thoughts might seem abstract, yet they touch something deeply human. The precision of gravity is not just a mathematical curiosity, it is the foundation of meaning in a physical sense. Because it is what it is, stars burn steadily enough for life to evolve, for memory to form, for minds to ask why. If we lived in a universe where gravity were stronger or weaker, we would not be here to measure it. Our very existence is written into the equations of general relativity, into the quiet strength of G. Still, fine-tuning leaves one question untouched. Why should the constants vary at all? Why should there be a range of possible values instead of one unbreakable truth? Some physicists believe that the constants emerge from the initial conditions of the universe, frozen at the moment of the Big Bang. Others think they are determined by deeper symmetries, mathematical relationships that lock certain ratios in place. In either case, the possibility of other universes remains open, for nothing in our current theories forbids them. If gravity is a product of geometry, and geometry can differ from one region of existence to another, then each universe might have its own version of curvature. Some could be more flexible, others rigid. Some might allow faster-than-light expansion, while others never inflate at all. In a few, gravity might act repulsively, pushing matter apart, instead of drawing it together. These are not idle speculations, but natural consequences of our equations once we allow the constants to vary. The picture that emerges is both humbling and liberating. We inhabit one thread in an immense tapestry, woven from countless possible combinations of numbers and laws. Our gravity is but one melody among infinite variations. It just happens to be the one that sings a harmony suitable for life. The next step in this journey is to explore how those alternate threads might arise. Inflationary cosmology suggests that the Big Bang was not a single explosion, but an ongoing process, where quantum fluctuations spawn entire universes. In that vision, every universe carries its own gravitational constant, its own curvature, and its own fate. To understand how gravity could differ elsewhere, we must look into that cosmic engine of creation, the multiverse itself. Every known constant in our cosmos is a delicate chord in the symphony of existence. Each note complements the others, forming harmony out of precision. Gravity, though soft-spoken, carries the rhythm. It sets the tempo at which galaxies swirl and stars breathe. The more we study it, the clearer it becomes that our universe is not simply built, it is tuned. Every structure, from an atom to a supercluster, depends on this near-perfect balance of numbers. If the early universe had expanded slightly faster, gravity would not have caught the newborn matter in time. There would be no stars, no planets, only a cold fog spreading endlessly into silence. If expansion had been slower, gravity would have reversed it all, collapsing the cosmos into itself long before time could take shape. The narrow space between those extremes, less than 1 part in a million, gave birth to everything. That balance is not coincidence. It is the mathematical miracle that allows history to exist. Within that balance lies another mystery. The universe is almost uniform in every direction, yet not perfectly so. The faint irregularities in the cosmic microwave background, the afterglow of the Big Bang, show where gravity first began to shape matter. Those tiny fluctuations, 1 part in 100,000, seeded galaxies, stars, and planets. If the variations had been smaller, structure would never have formed. If larger, the universe would have turned chaotic. Gravity tuned itself to amplify just enough disorder to create beauty. It is tempting to call this perfection design, but physics offers a subtler possibility. Inflationary theory suggests that our universe began as one small region within a vast, rapidly expanding field of energy. Quantum fluctuations within that field could have created countless other regions, each with its own laws and constants. In some of them, gravity might be stronger or weaker. In others, it might behave in ways entirely alien to us. Most of those universes would be empty, lifeless, and short-lived. Ours simply happens to be one where gravity allows endurance. This view replaces the need for intention with the power of variation. If enough universes exist, every possible configuration of constants must appear somewhere. Life, in this vast landscape, is not planned, it is inevitable. In that sense, gravity's perfection is not a miracle, but a statistical truth. We are the witnesses who emerged in one of the rare universes where the equations permitted complexity. And yet, even this explanation leaves wonder intact. To imagine a multiverse is to accept that our gravity is not universal at all, but one instance in a grand ensemble. Perhaps there are universes where gravity pulls sideways instead of inward, or where it acts only within short distances. Perhaps there are places where mass repels mass, scattering matter instead of binding it. Some of these realms might be entirely invisible to us, their geometry folded beyond our perception, their timelines running too fast or too slow to ever intersect with ours. In the fine-tuned universe, gravity is both sculptor and storyteller. It carves the stage on which time performs, then records every act upon the curvature of spacetime. Each star that forms, each orbit that holds, each collapse that ends a cosmic life, all are written in its invisible script. To think of gravity is to think of memory, of persistence, of the way the universe remembers its own shape. We live inside that memory. Every second that passes is measured by the curvature of space-time around us, and every movement we make is a small ripple in the same field that bends the light from distant galaxies. The constancy of gravity is what allows the concept of time itself to have meaning. If it changed from moment to moment, reality would become incoherent, like a song that forgets its rhythm halfway through. This constancy, this delicate order, may be rare. If other universes exist, most would not share it. But perhaps some do. Worlds where gravity still curves space-time, though with different strength or scale, leading to structures as complex and alive as ours. The possibility that other universes might also feel the pull of their own gravity, their own version of connection, is one of the most humbling ideas in science. It means that even if we are unique, we are not alone in principle. Our understanding of gravity's fine-tuning is still incomplete. We can measure its strength, trace its influence, and simulate its behavior, but we cannot yet explain why it is what it is. It may be that the answer lies forever beyond our horizon, locked within the geometry of the multiverse. Or perhaps the deeper truth is simpler. Gravity is the way the universe organizes itself, a natural consequence of existence. As we look ahead, the question grows larger. If there are countless universes, each with its own constants, how does gravity vary among them? Could there be universes where gravity dominates, crushing everything into singularity, or universes where it scarcely exists at all? Could there be forms of matter and life shaped by those alien versions of curvature, evolving under laws utterly unlike our own? The next step in this journey is to explore that grander stage, the multiverse. To understand how inflation could have spawned endless universes, each with its own geometry, and how gravity might shift and transform across them. There, among infinite possibilities, we might find reflections of our own reality or something entirely beyond comprehension. Imagine standing on the edge of the known universe, where galaxies fade into darkness and the faint afterglow of the Big Bang still hums like a distant echo. Beyond that darkness, science now dares to suggest there may lie more universes, realms with their own skies, their own laws, their own versions of gravity. The multiverse is not an invention of fantasy. It is a possibility born from the mathematics of cosmology itself. In the beginning, our universe was smaller than an atom, a dense sea of energy seething with quantum fluctuations. Within that primordial storm, regions of higher density began to expand faster than their surroundings. According to the theory of cosmic inflation, proposed by Alan Guth in the 1980s, this expansion was not merely fast, it was exponential. In less than a fraction of a second, space grew by an unimaginable factor, stretching quantum irregularities into the seeds of galaxies. Inflation ended in our region, allowing matter and light to form, but elsewhere, it may have continued forever. This eternal inflation creates a cosmic foam of universes. Each bubble forms when inflation stops in one region, releasing its energy into a burst of creation, a Big Bang. Our observable universe is one such bubble, floating in an endless sea of others. Each bubble may have its own physical constants, its own arrangement of particles, even its own version of space-time geometry. Gravity in those universes could be stronger, weaker, or different in kind. In this view, reality is far larger than what we can observe. The observable universe, spanning about 93 billion light-years, is a single grain of dust in a boundless landscape. We cannot see the other universes because they are beyond our cosmic horizon. Light from them will never reach us. Yet the mathematics of inflation suggests they exist, and their diversity could explain the fine-tuning of our own world. To understand how gravity might differ in those other realms, one must see inflation not as a singular event, but as a process that never truly ended. The energy field driving inflation, known as the inflaton, can fluctuate quantum mechanically. Where its energy remains high, space continues to expand exponentially, creating new regions of spacetime. Where it drops, a universe like ours is born. Because quantum fluctuations vary randomly, each universe inherits different values for its fundamental constants. In some bubbles, the gravitational constant could be larger, causing matter to collapse into black holes before stars can form. In others, it could be smaller, leaving a diffuse fog of gas that never condenses. Some universes might have no stable atoms at all. Others could form matter so dense that time slows to a crawl. Each universe would feel the same underlying physics expressed through different parameters, producing endless variations on the theme of gravity. The idea of multiple universes once belonged to philosophy, but inflationary cosmology gives it a mathematical foundation. It is not speculation for its own sake, but a natural consequence of equations that already explain what we observe. The pattern of cosmic microwave background radiation, the distribution of galaxies, and the flatness of spacetime all support the inflationary model. If inflation happened once, there is no reason to think it happened only here. String theory adds another layer to this picture. It predicts a vast landscape of possible vacuum states, perhaps 10 to the power of 500 or more, each corresponding to a different configuration of the extra dimensions beyond our four. Each configuration defines a distinct universe with its own constants and physical laws. Gravity, which arises from the shape of those dimensions, could behave differently in each one. In some, it might be confined to a brain like ours. In others, it could spread freely through higher dimensions, altering its apparent strength. This vast collection of possible universes is sometimes called the multiverse landscape. Within it, our universe is a local valley, stable enough for matter and life, but not necessarily unique. Other valleys could have deeper energy levels, others shallower. The multiverse becomes a terrain of infinite possibility where gravity takes on every form that mathematics allows. To many, the multiverse feels unsettling. It challenges the idea of a single, self-contained reality. But for physicists, it offers an elegant way to explain why our constants seem fine-tuned. If all possible universes exist, we should not be surprised to find ourselves in one where gravity allows complexity. It is the same logic that explains why life on Earth finds itself between freezing and boiling temperatures. In other conditions, it could not survive to ask the question. Still, evidence remains indirect. We cannot yet observe other universes directly, though some researchers have proposed ways to detect their influence. If another universe collided with ours in the distant past, the impact might have left a circular imprint in the cosmic microwave background. If gravity leaks between universes, it might subtly distort the motion of galaxies. None of these signatures has been confirmed, but the search continues. The multiverse hypothesis does not diminish the wonder of our own universe. It expands it. To imagine countless realities, each sculpted by gravity in its own way, is to realize how vast creation might be. Ours is one arrangement among an infinity of possibilities, one tune in the endless symphony of existence. If other universes do exist, then gravity itself becomes a universal storyteller, retelling the same theme with endless variations. In one universe, it may collapse everything into eternal darkness. In another, it may barely touch matter at all. Somewhere between those extremes lies ours, a universe where gravity holds just tightly enough to let stars shine and minds emerge to ponder it. But to see how gravity could change across universes, we must first imagine what happens when it is altered deliberately, when its strength is turned up or down, when space-time bends more sharply or scarcely at all. The next step is to explore those hypothetical realms, worlds where gravity is stronger, where it is weaker, and what that means for the possibility of life and structure. If the multiverse exists, then reality is not a single story, but an infinite library of them. Each universe would be a book with its own physics, written in a different language of constants. Some volumes would be too short to tell a tale, collapsing the moment they begin. Others might stretch endlessly, too diffuse to ever form structure. Our universe would be one of the rare pages where the words align in a way that makes meaning possible. Gravity, in this grand collection, would be a recurring theme, sometimes soft and slow, sometimes wild and unbound, sometimes unrecognizable. To understand how gravity might differ across those countless worlds, imagine the mechanism that births them. During the earliest moments of creation, the universe expanded faster than light through a process known as inflation. This expansion was driven by a field of immense energy that filled all of space. Like the surface of boiling water, it was unstable, bubbling and fluctuating. Each bubble that formed marked the end of inflation in one region, giving birth to a universe with its own distinct physical properties. Our universe is one such bubble, and beyond its horizon, others continue to form even now. Each new universe cools and stabilizes into its own pattern. Some bubbles may inflate longer, stretching their space more and freezing in different energy densities. That difference alone could alter gravity's strength or even its nature. In some regions, the gravitational constant might be immense, drawing matter together before it can spread. In others, the curvature of space-time might be so gentle that stars never ignite. Between those extremes, there would be universes that mirror ours in structure but differ in detail. Galaxies of different shapes, stars of different brightness, perhaps even forms of matter bound by a gravity we could scarcely imagine. The scale of this idea is staggering. If inflation is eternal, then the number of universes is infinite. Somewhere, there could be a universe almost identical to ours, differing only in the mass of an electron or the density of dark energy. Somewhere else, gravity could be repulsive, pushing matter apart rather than binding it. Each variation changes the story written across the fabric of space-time, shaping whether complexity can arise or whether chaos reigns. Physicists have tried to describe this endless landscape mathematically. In string theory, for instance, the extra dimensions beyond the familiar four can be curled up in countless ways. Each configuration corresponds to a different vacuum state, with its own physical constants and laws. The number of possible configurations is so vast, estimated at roughly 10 to the power of 500, that it becomes natural to think of every version as real. In that framework, gravity is not a single force, but a family of relationships between geometry and energy, each determined by the structure of its dimensions. Some versions of the multiverse might allow more than 3 spatial dimensions. In those higher dimensional worlds, gravity could spread across additional directions, making it appear weaker when measured by beings confined to fewer dimensions. This idea, explored in models like those of Lisa Randall and Raman Sundram, suggests that our universe might be a 4-dimensional surface floating within a 5-dimensional space. Gravity could leak between these layers, explaining why it is so faint compared to the other forces. If such leakage occurs, then the gravity we feel could be only a shadow of a stronger interaction existing in higher dimensions. In other regions of the multiverse, those extra dimensions might curl differently or not at all, changing gravity's range and strength entirely. Universes with tightly curled dimensions could have crushingly strong gravity, while those with open dimensions could be nearly weightless. The shapes of those dimensions, the way they fold and twist, determine how gravity emerges. Each geometry gives rise to its own curvature, its own version of Einstein's equations. These possibilities may sound distant, yet they emerge from the same mathematics that describes our own cosmos. The equations of general relativity and quantum field theory, when extended to include inflation and extra dimensions, naturally predict a multiverse filled with diverse gravitational behaviors. None of this violates known physics, it merely stretches it to its logical limits. And if that logic is correct, then gravity is not universal at all. It is local, specific to the bubble of space-time we inhabit. What we call the law of gravity might be only one dialect among countless others, each expressed through its own geometry. Somewhere, perhaps, there are universes where time flows differently, because gravity distorts it in ways we cannot conceive. Somewhere, black holes might not exist because space-time never curves enough to trap light. Somewhere, gravity might run backward, driving expansion instead of collapse. For now, we cannot test these possibilities directly. The horizon of our universe limits what we can see, and no signal can cross from one bubble to another without being stretched into nothingness by inflation. Yet scientists have begun to search for subtle traces, patterns in the cosmic microwave background that might hint at collisions between universes or deviations in gravitational strength that suggest hidden dimensions. So far, the evidence is silent, but silence in science is not the same as absence. It is the pause before discovery. The multiverse hypothesis transforms our understanding of gravity from an absolute truth into a variable story. It suggests that what we call the fabric of space-time is only one of many ways the cosmos can weave itself. Gravity becomes a rule that depends on the conditions of creation, a reflection of how the universe cooled, how its dimensions folded, how its constants settled. To comprehend the implications of this idea, we must venture deeper into the thought experiment. What happens if we step inside one of those other universes where gravity differs from our own? How would stars behave? How would time flow? Could anything like life exist? The next step is to imagine those possibilities, not as fantasy, but as scientific exploration. We will begin by visiting universes where gravity is stronger than in ours, where curvature dominates and every moment teeters on the edge of collapse. If one could travel across the multiverse, passing through the endless foam of expanding bubbles, the journey would not be a voyage through distance, but through possibility. Each transition from one universe to another would feel like crossing a boundary between laws, stepping from one reality's geometry into a completely different one. Gravity, the most familiar companion of all, would not remain constant on this journey. It would shift and change, rewriting the rhythm of motion and the meaning of mass. Imagine entering a universe where gravity is far stronger than it is here. The first thing you would notice is time itself slowing. In Einstein's theory, time and gravity are inseparable. A stronger curvature of space-time means a deeper well in which time runs slower. In such a universe, seconds might stretch into hours, and the dance of matter would unfold in a kind of cosmic slow motion. Yet the beauty of that world would be fleeting, for strong gravity is not gentle. It crushes and consumes, shaping everything into compact forms and shortening the lifespan of stars. In that universe, planets could scarcely exist. Any attempt at formation would end quickly, as gravitational collapse would overcome pressure before stable orbits could form. The first clouds of gas born from the Big Bang would collapse rapidly, creating enormous stars that burn with blinding fury for a brief instant before imploding into black holes. Those black holes would dominate the sky, merging and swallowing until the universe itself grew dark, its matter trapped behind horizons. From a distance, such a cosmos might look calm, filled with quiet darkness, but beneath that calm lies chaos, matter in constant collapse, space torn by singularities, time distorted beyond recognition. No chemistry could survive there, no gentle cycles of formation and decay. Gravity, too strong for balance, would silence the orchestra before it could play a note. Now imagine drifting onward into another universe, one where gravity is far weaker. There, space-time is almost flat, its curvature too faint to gather matter into clusters. The early universe would expand endlessly, its particles scattering without ever condensing into stars. Light would travel forever through an empty haze, never encountering anything to warm or illuminate. Time would move freely, but nothing would mark its passage. Without gravity's guidance, there would be no orbits, no suns, no seasons. The cosmos would be pure stillness, an ocean of light and cold hydrogen stretching into eternity. Between these extremes lies a narrow corridor, the range of balance where gravity is neither too strong nor too weak, where stars live long enough to forge the elements of life. Our universe occupies that corridor. In the vast multiverse, such stability might be rare, perhaps even unique, yet it is precisely what allows us to exist and to wonder about it. Some universes in this endless landscape could have completely different relationships between gravity and the other forces. In a few, gravity might interact directly with electromagnetism, creating phenomena where light itself curves more violently than it does in ours. In others, gravity might not depend on mass, but on energy flow, pulling harder on heat or radiation. There could be universes where gravity is repulsive on small scales, but attractive on large ones, creating strange pockets of structure surrounded by emptiness. The equations allow such possibilities, even if they seem alien to human intuition. If space can inflate endlessly, spawning new universes with different constants, then gravity is not a single law, but a family of behaviors, each born from the way the inflaton field decays. Our universe's version of gravity may be one stable configuration among many unstable ones. Some configurations lead to expansion, others to collapse. Some universes might flicker into existence and vanish again within moments, never cooling enough for atoms to form. Others could expand forever, their gravity too weak to hold them together. There may even be universes where space-time itself does not exist in the form we know. If gravity arises from geometry, then changing the dimensionality of that geometry changes everything. A universe with only two spatial dimensions could not sustain orbits. The gravitational potential would behave differently, making stable structures impossible. A universe with more than 3 dimensions might allow gravity to spread too thinly to form stars. The familiar dance between attraction and inertia, between collapse and balance, would not occur. Every possibility permitted by mathematics seems to find expression somewhere in the multiverse. It is a vision of existence so vast that the human mind can barely hold it. Yet within this infinity, gravity remains the common thread, the principle that defines how each universe organizes itself. Whether it pulls, pushes, or fades, gravity shapes the stage upon which every form of matter performs. Though we cannot travel between universes, we can trace their outlines through the logic of physics. The full equations of inflation, relativity, and quantum theory together suggest that the multiverse is not just a philosophical dream, but a physical consequence. It tells us that our gravity, the gentle, steady curvature that holds galaxies together and keeps our feet on the ground, is one note in a symphony of infinite variations. To understand what those variations mean, we must take the next step and imagine universes where gravity itself changes, not merely in strength, but in nature. In the chapters ahead, we will explore such realms, some where gravity dominates like a storm, others where it barely whispers, and still others where it emerges from deeper structures unlike anything known. For now, we close this chapter with the realization that our universe, vast as it seems, may be only a single ripple in an eternal sea of space-time, each wave governed by its own version of gravity's law. Imagine a universe where every atom feels the pull of gravity 1,000 times more intensely than in ours. The stars in that universe ignite quickly and die young, their lives compressed into moments of furious brilliance. Matter collapses into compact forms almost as soon as it gathers. Space bends sharply around even the smallest objects, and the rhythm of time slows to a crawl near every source of mass. To live in such a universe would be to exist under an unending weight, not only of force, but of inevitability. Gravity would no longer be the quiet sculptor we know. It would be the hammer of creation, shaping and destroying with equal power. In our universe, gravity balances delicately against the forces that resist collapse. Gas clouds condense until nuclear fusion ignites, creating stars that shine steadily for billions of years. But increase the gravitational constant even slightly, and that balance breaks. Gas would collapse before pressure could stabilize it. Stars would form rapidly, fuse their fuel at immense rates, and die in violent explosions. Supernovae would be common, black holes abundant, and long-lived worlds rare. A stronger gravity means denser stars, shorter cosmic lifespans, and a universe that burns through its potential almost as soon as it begins. Planets, if they managed to form, would orbit close to their stars, their paths twisted by the intense curvature of space. Tidal forces would be extreme. Moons would be ripped apart, and oceans would surge with the pull of nearby masses. The landscapes of such worlds would be in constant motion, their crusts strained by relentless gravitational stress. Mountains might rise and collapse in cycles of hours rather than millennia. Even time itself would flow unevenly, stretching and compressing in ways that make memory unreliable. In a universe of strong gravity, black holes would dominate. The first generation of stars would leave behind immense remnants, each pulling on the fabric of spacetime with overwhelming strength. Galaxies, if they could form at all, would be smaller and more compact, their centers brimming with gravitational monsters devouring everything around them. Light would struggle to escape these dense regions, and much of the cosmos would exist in darkness. The delicate spiral arms we see in our galaxies would never appear. Gravity would sculpt the stars into thick, spherical clusters or collapse them entirely. Time in such a cosmos would feel different. Near a black hole, seconds could stretch into years relative to distant space. In a universe where black holes are everywhere, this time dilation becomes the norm. The entire history of the cosmos might unfold in what, from our perspective, would seem like an instant. Observers within that universe, if they could exist, would experience their surroundings as stable, yet from afar, their whole existence would pass like a spark. Gravity strong enough to curve time so steeply turns eternity into a brief flicker. What would such strength mean for life? Complex chemistry requires stability. Planets must orbit for long periods, temperatures must remain within narrow ranges, and stars must burn slowly enough for evolution to occur. In a stronger gravity universe, those conditions vanish. Orbits decay quickly, stars collapse before they can nurture life, and radiation from constant supernovae sterilizes everything. Even if life began, it would have little time to evolve. Existence in such a cosmos would be fleeting, perhaps lasting only until the next collapse reshaped the stars themselves. Yet even a violent universe has beauty. Strong gravity reveals the structure of space-time in its rawest form. Gravitational waves would ripple constantly, crossing one another in an intricate cosmic choreography. The sky would shimmer with distortions, light bending and twisting through fields of curvature. Space would no longer seem empty, but alive, a dynamic fabric that dances with motion and collapse. Physicists studying hypothetical universes like this often explore how the constants of nature interact. Gravity does not act alone, it balances against the electromagnetic and nuclear forces. If gravity grows stronger while the others remain constant, matter itself becomes unstable. The pressure inside atoms would no longer resist gravitational compression, and matter might collapse into degenerate forms, creating neutron-rich structures or even micro-black holes. The universe would be filled not with atoms, but with dense fragments of collapsed matter, perhaps the size of mountains yet heavier than entire worlds. Some cosmological models suggest that a strong gravity universe could still achieve temporary equilibrium through expansion. If the rate of cosmic expansion also increased proportionally, the two effects might balance for a time. Stars could form, though shorter-lived, and galaxies might persist for brief eras. But such balance would be precarious. Even a small fluctuation could tip the system toward collapse or dispersal. Stability would be as fragile as a flame in a storm. One fascinating consequence of stronger gravity would be the alteration of cosmic background radiation. In our universe, the afterglow of the Big Bang cooled slowly, allowing matter to separate from light and form structures. In a universe with stronger gravity, that separation would occur faster, compressing the timeline of cosmic history. Structures would form early but fade quickly. the night sky would grow dark, long before any observers could arise to see it. This raises an important question about the relationship between gravity and time. In relativity, gravity is not just curvature of space, but of space-time itself. Strengthening gravity means deepening that curvature, which also deepens the flow of time. A universe with stronger gravity would be one where time itself feels thicker, more resistant to change. Events would unfold slower for local observers, but the overall lifetime of the cosmos would be shorter in the grand view. This paradox of slower moments within a faster destiny is one of the most haunting implications of gravitational variation. Could intelligence exist in such a realm? Perhaps, but not as we understand it. If life could adapt to rapid change and extreme density, it might evolve as patterns within energy fields rather than biological forms. Some scientists have speculated that in extreme gravitational environments, information could be stored in the spin and curvature of space-time itself. Consciousness, if it appeared, would be tied to gravity rather than matter, existing as waves in the geometry of the universe. A stronger gravity cosmos would also alter the perception of scale. Mountains would flatten under their own weight, oceans would compress, and even gas would behave like liquid under the immense pull. Architecture, if any civilization could build, would need to counter constant stress. Creatures would be compact, low to the ground, and built for endurance rather than speed. The sky, heavy with gravitational lensing, would reveal multiple images of the same star, distorted and shimmering like reflections on curved glass. From a cosmic perspective, such a universe would live fast and die young. Stars would exhaust their fuel, galaxies would merge, and black holes would consume the remnants. Eventually, those black holes would evaporate through Hawking radiation, releasing the last traces of energy back into space. The universe would end as it began, dense, hot, and uniform. But its entire history would have passed in what, to us, might seem no more than a blink. By contrast, our universe feels almost tranquil. Gravity's weakness allows complexity and endurance. Yet the thought of stronger gravity reminds us that this calm is not inevitable. It is one choice among many in the grand pattern of existence. The multiverse, if real, may contain countless universes that lived and died in gravitational storms before ours ever began. Each would be a variation on the same equation, a different melody in the cosmic symphony. The next step in this exploration takes us to the opposite extreme, a universe where gravity is weaker, where matter struggles to find itself, and the stars that light our skies would never be born. There, existence becomes a whisper rather than a roar, a slow drift through endless expansion. Now imagine the opposite of everything we know, a universe where gravity is not a sculptor but a suggestion, so faint that matter barely acknowledges its presence. Clouds of gas drift eternally without ever collapsing into stars. Light travels endlessly through transparent emptiness, never meeting dust, never warming a world. Time stretches wide and uneventful, not because it is slowed by curvature, but because nothing ever happens to mark its passage. Such a universe would be vast, serene, and almost completely silent. In our cosmos, gravity is weak compared to the other forces, yet it is strong enough to shape galaxies and birth suns. If it were weaker still, say by a fraction so small as 1 part in a trillion, those same galaxies would never form. The expansion that began with the Big Bang would continue unchecked, scattering atoms too far apart for any meaningful structure to arise. Hydrogen and helium would fill space like a thin mist, but no gravity well would ever gather them. The universe would be nothing but a diffuse cloud, growing colder and darker forever. The first few moments after the Big Bang decide everything. When the universe expands, 2 opposing influences compete: gravity pulling matter inward, and the outward push of momentum and radiation. In our universe, those 2 balance delicately, allowing the formation of galaxies. But in a weaker gravity universe, The outward motion wins easily. Space would stretch faster than matter could clump. No stars would ignite, no planets would form, and no cycles of energy or life could begin. The cosmos would exist, but it would be empty in every meaningful sense of the word. Even if some faint clumping occurred, the results would be ghost-like. Without sufficient gravitational pull, gas clouds would never compress enough for nuclear fusion to begin. There would be no starlight, no heat, no chemistry beyond the simplest molecules. Without stars to create heavier elements, there would be no carbon, oxygen, or iron, no material for complexity. Everything would remain primordial, frozen in its simplest form. Time in such a universe would have no rhythm. Without the gravitational curvature that binds motion into cycles, planetary orbits, stellar lifetimes, galactic rotations, there would be no repeating patterns, no sense of progression. The passage of time would be meaningless, because nothing would ever change. Temperature gradients would vanish, leaving no source of energy flow. Entropy would remain nearly constant, and with no events to mark it, existence would feel eternal, but lifeless. Astronomers studying cosmic expansion have found that our universe teeters on this very edge. Gravity's pull barely restrains the expansion driven by dark energy. If dark energy were slightly stronger, our fate would match that of a weaker gravity cosmos. Galaxies would drift apart faster than light could cross between them. Eventually, each star system would find itself isolated in an ever-accelerating void. The night sky would empty until every point of light faded beyond visibility. The cosmic web that connects galaxies would unravel strand by strand. In an even weaker gravity universe, that isolation would begin immediately. No galaxies would ever form, no suns would ever shine. The cosmic background radiation would cool rapidly, plunging the universe into darkness before it could reach 1 billion years of age. There would be no black holes, no supernovae, not even the faint glow of dying stars. Matter would simply drift. The only light would be the fading echo of the Big Bang itself. Yet even this stillness carries a strange beauty. Without gravity's compression, space would be smooth beyond imagination, an unbroken fabric of geometry expanding forever. The curvature of spacetime would be so mild that parallel lines would never converge. Light would travel in perfect straight paths, undistorted by lensing or deflection. It would be a universe of pure geometry, where Einstein's equations reduce to the simplest possible form. A cosmos without drama, without tension. A flat and endless stage upon which no play is performed. Some physicists have speculated that such universes might still allow alternate forms of organization. Perhaps quantum fluctuations could create temporary density ripples, brief regions of structure that appear and fade. In that case, tiny sparks of complexity could arise momentarily, microscopic pockets where time flows differently before dissolving again into uniformity. But these would be brief illusions, not worlds. They would lack the permanence that gravity provides. In our own universe, weak gravity governs more than we realize. It allows stars to live long enough for life to evolve, but it also allows cosmic expansion to continue. If gravity were slightly weaker, expansion would dominate completely. The cosmic microwave background would stretch so quickly that its faint warmth would vanish almost instantly. The universe would reach thermal equilibrium, perfect uniform temperature, before complexity could even attempt to arise. The concept of a weaker gravity cosmos also reveals how interdependent the laws of physics are. Gravity does not exist in isolation. It interacts with the electromagnetic and nuclear forces that hold matter together. If gravity weakens while the others remain the same, structures like atoms and molecules would remain stable, but they would exist alone, scattered through infinite emptiness. There would be no gravitational wells to gather them, no stars to recycle them. It would be a cosmos of individual, disconnected particles, a universe that exists without relationships. Philosophically, such a universe challenges our idea of meaning. In our world, gravity connects everything. It gives context to distance, to mass, to time. Without it, every atom becomes an island, alone and indifferent. Existence would be stripped of interaction, and interaction is what gives rise to experience. Without gravity, there would be no curvature, and without curvature, there would be no story. One might imagine beings of pure thought, formed from quantum fluctuations, observing such a world. They would find no motion, no birth, no death, only the endless stillness of unchanging expansion. To them, time would be indistinguishable from space, and existence would feel like a single frozen moment. In that sense, a universe with very weak gravity is not a place but a state, an eternal now. As cosmologists model these weaker gravity scenarios, they find that our universe sits on a razor's edge. The gravitational constant we measure allows the perfect balance between collapse and expansion, between chaos and emptiness. Change it slightly in either direction, and the cosmos becomes sterile. This sensitivity suggests that our universe may not be random at all, but part of a deeper pattern in which only a narrow band of gravitational strengths can support complexity. If the multiverse exists, perhaps most universes fall outside that band. They are either too heavy and short-lived, or too light and silent. We inhabit one of the rare realms where gravity's pull is just strong enough to shape matter, but gentle enough to let it endure. In that sense, gravity is not only a physical constant, but a condition for existence itself, a universal threshold between being and nothingness. In the next exploration, we move beyond strength entirely. What if gravity did not merely vary in magnitude, but changed in nature? What if space-time itself were different, composed of discrete pieces or entirely absent as we know it? To answer that question, we must leave behind the familiar continuum of relativity and venture into the quantum depths where geometry breaks apart and gravity may arise from something far stranger. To imagine a universe without our familiar space-time is to step beyond the horizon of intuition. Everything we know, from falling apples to orbiting galaxies, is written into the geometry of four-dimensional space-time, three of space and one of time. Einstein's general relativity taught us that gravity is not a force pulling at a distance, but the curvature of that geometry itself. But what if, in some other universe, there were no continuous space-time at all? What if reality were not smooth, but granular, stitched together from discrete fragments at the smallest possible scales? In our universe, space-time appears continuous because we cannot see its foundation. The Planck length, about 1.6 times 10 to the power of negative 35 meters, is so small that no experiment can probe it directly. Yet many physicists suspect that below this scale, the fabric of the universe becomes pixelated, like a digital image viewed too closely. Loop quantum gravity, one of the leading attempts to unify general relativity with quantum mechanics, proposes that space is made of finite loops woven into a network. Each loop carries a quantum of area or volume, and together they create the illusion of smoothness. If that theory is right, then gravity is not the bending of a continuous sheet, but the result of how these loops connect and interact. In another universe, the size of those quanta could be larger, making space-time visibly granular. Distances would not be continuous. Objects could move only in discrete jumps from one point to another. Time itself might tick rather than flow, advancing in indivisible intervals. Such a universe would feel strange to its inhabitants. Light would not travel in perfect waves, but in packets of motion, and causality might blur at the edges, since there would be no perfectly smooth path between events. Alternatively, space-time might not exist at all in its familiar sense. Some theories, such as those involving holographic principles, suggest that space and time could emerge from deeper layers of quantum information. In the framework known as ADS-CFT, for example, a universe with gravity can be mathematically equivalent to a lower dimensional world without gravity, but with quantum entanglement between its particles. In this view, The geometry of space-time arises from patterns of entanglement. Gravity becomes not a fundamental force, but a side effect of quantum information organizing itself. If that is true for our universe, then other universes might have different rules for how information connects. Their space-time could be built from different kinds of networks, ones that produce different curvatures or none at all. Imagine a cosmos where entanglement forms closed loops rather than continuous webs. The resulting geometry might curve in ways impossible in our universe, giving rise to gravity that repels instead of attracts. Or imagine a network where information connections constantly shift, causing gravity to fluctuate unpredictably. In such a reality, orbits would never be stable, and the idea of distance itself might lose meaning. String theory offers another picture. It suggests that what we call space-time is not fundamental, but a vibration of one-dimensional strings moving through higher dimensions. These strings can stretch, twist, and merge, giving rise to particles and forces. Gravity in this framework comes from a special vibration mode called the graviton. But the shape of the extra dimensions, how they are curled and compactified, determines how gravity behaves. In our universe, those dimensions are tiny and stable. In another, they might be vast or dynamic, causing gravity to oscillate or vanish altogether. Some string theory models even allow universes where space-time itself is an emergent property of string interactions, not an initial condition. If such a universe exists, its physics would be profoundly alien. There would be no fixed background against which events occur. Instead, geometry would arise only when energy or matter interacts. Between interactions, there would be nothing. No distance, no duration, no here or there. Space and time would be relational, existing only as a consequence of activity. From our perspective, such a world would seem frozen, yet within it, change could still occur in a form beyond our comprehension. Some theories go further, suggesting that gravity itself might emerge from entropy. Eric Verlinder's concept of entropic gravity proposes that gravity arises from the tendency of information to spread. In this view, space-time curvature is a statistical effect of microscopic degrees of freedom-seeking equilibrium. If that principle holds, then a universe with different information laws could have entirely different gravitational behavior. One cosmos might have no attraction at all, another might see gravity reverse its direction, pulling less dense regions toward more dense ones. In a universe without continuous space-time, motion would no longer be a smooth transition from one place to another, but a sequence of quantum hops. The idea of a straight line or a circular orbit would lose its meaning. Objects might appear and disappear between quantized positions, their paths defined only probabilistically. The classical idea of inertia would fail, and with it, the familiar sense of cause and effect. Such universes challenge even the concept of time. If time emerges from change, then in a reality where nothing moves smoothly, time itself might be discontinuous. Events could occur in fragments, separated by intervals of non-existence. An observer within that universe might not perceive these gaps, experiencing instead a flickering continuity like frames in a film. But on a deeper level, reality would be built from moments that do not flow into each other, but coexist as separate nodes of possibility. This perspective suggests that gravity, as we know it, is only one form of connection among many. It links energy and geometry in a universe where space and time are continuous. But if continuity itself can differ, then so can gravity's nature. There might be universes where gravity behaves like magnetism, aligning rather than attracting. Others could have topologies where objects loop back on themselves, creating regions where gravity cancels entirely. In a few, the distinction between matter and space could vanish, everything being part of one unified field. Even in our own universe, we may be glimpsing hints of this deeper structure. Quantum fluctuations of space-time, known as foam, are predicted to occur at the Planck scale, constantly warping geometry in minute ways. If those fluctuations could be magnified, they might reveal the discrete, information-based foundation of gravity. In another universe, those fluctuations might dominate, making space-time turbulent even on large scales. The night sky there would shimmer not because of starlight, but because of space itself, rippling like an ocean. The idea of universes without our kind of space-time may sound abstract, but it follows naturally from the quest to unify gravity with quantum mechanics. When we push the equations to their limits, smooth geometry breaks down, and something else must take its place. That something, whether it is loops, strings, or information networks, could define the nature of gravity in realms beyond our own. To live in such a universe would be to exist not in space, but within a web of relationships. Not in time, but in a sequence of informational states. Motion, distance, and gravity would be reinterpreted as connections between patterns rather than interactions between objects. Perhaps consciousness itself, which depends on patterns of information, would feel at home there. Perhaps such a universe would think rather than move, and its gravity would be the logic that holds its thoughts together. In contemplating these possibilities, we see that our version of gravity is only one interpretation of a deeper truth. Whether continuous or discrete, emergent or fundamental, gravity reflects how reality organizes itself. It is not just curvature, but coherence, the way the universe keeps its structure intact. In other universes, that coherence could take other forms, giving rise to alien geometries where existence itself feels different. And yet, even in those unimaginable worlds, the principle remains. Something binds, something connects, something gives order to chaos. That something is gravity, or whatever name it takes beyond our space-time. Every law of nature in our universe is rooted in geometry. Gravity, magnetism, motion, even the passage of time, all arise from the shape of the space they inhabit. When we speak of curvature, we speak of destiny. The path that a planet takes around a star, the way light bends around a galaxy, or how black holes trap time itself, all depend on how geometry behaves. But what if that geometry were not the same everywhere? What if other universes, formed from the same fundamental mathematics but different initial conditions, obeyed their own geometrical rules? In our cosmos, space has 3 dimensions and time adds a 4th. This combination allows stable orbits and predictable trajectories. It gives us both freedom and constraint, a balance between expansion and structure. But in a universe with fewer dimensions, gravity cannot form the same shapes. In a 2-dimensional world, mass would curve space differently. A planet could not orbit a star because the force of attraction would fall off too sharply with distance. Every object would either spiral inward or escape entirely. There would be no stable paths, no circular motion, only collision or flight. Such a universe could not build complexity. Without stable orbits, stars could not form systems, and planets could not linger near warmth long enough for life to arise. The geometry itself forbids permanence. Everything would be fleeting, a flash of energy, then dispersal. Yet even there, gravity would still exist in some form. It would not curve a 3-dimensional space, but distort a plane, creating patterns of flow rather than spheres of attraction. The simplicity of that world would make it elegant, but lifeless. Now imagine the opposite, a universe with more than 3 spatial dimensions. In such a realm, gravity weakens faster with distance because the force spreads through more directions. This means that objects would struggle to hold together. Galaxies might never form, planets could not orbit for long, even atoms might lose their stability. The familiar structures of our world would dissolve into chaos. And yet, at the same time, higher dimensions open doors to behaviors that defy our intuition. Some versions of string theory propose that our universe is a 4-dimensional brain, short for membrane, embedded within a higher dimensional space called the bulk. The bulk might contain 5, 6, or even 11 dimensions, depending on the model. In this framework, gravity is unique because, unlike the other forces, it can move freely through those extra dimensions. That could explain why gravity is so weak compared to electromagnetism and the nuclear forces. It is not confined to our brain, but spread across the larger bulk. If this idea is correct, then other brains could exist nearby, each hosting its own universe. Their matter would be invisible to us, because light and electromagnetism cannot cross between brains, but gravity could. Its influence would leak subtly across the higher dimensional space, tugging at our cosmos in ways we might detect. Some scientists have speculated that the mysterious dark matter we infer from galactic rotation could be a shadow of gravitational effects from a neighboring brain. If so, then our universe is not isolated, but part of a layered structure, a cosmic stack of realities bound together by shared geometry. The mathematics of such geometries predicts strange phenomena. In the eye, Randall's sundrum models, for instance, the extra dimension can be warped rather than flat. This warping changes how gravity behaves across distances, making it appear weak in our universe, but strong at microscopic scales. If true, it would mean that the geometry of space itself modulates the strength of gravity. In other universes with different warping, gravity might dominate completely or vanish almost entirely. Geometry would decide fate. It is difficult to visualize higher dimensional curvature, but we can glimpse its logic. Just as a two-dimensional being would see only the cross-section of a three-dimensional object, we perceive only slices of higher dimensional structures. The true form of gravity might extend beyond what we can ever observe. If the bulk around our universe is curved in complex ways, the gravitational field we measure could be only the projection of a larger, multi-dimensional pattern. This realization changes how we think about distance and motion. If gravity propagates through extra dimensions, it could connect regions of space that appear far apart in our three-dimensional view. 2 points separated by billions of light years might be close in higher dimensional terms, linked by shortcuts through the bulk. In such a geometry, gravity could act almost instantaneously across what seems like vast separation, not by breaking the speed of light, but by traveling through unseen routes. Wormholes and bridges through space, long considered science fiction, might simply be features of multidimensional geometry. In universes where the number of dimensions differs, even the meaning of mass could change. Mass, after all, is just the measure of how much an object curves spacetime. In a five-dimensional world, the same amount of energy might produce a completely different degree of curvature. Stars might be tiny but immensely heavy, or vast, yet nearly weightless. Black holes could take forms unimaginable to us, rings, sheets, or higher dimensional surfaces called black brains. Some might have more than one event horizon, enclosing nested layers of space and time. The geometry of such universes would not only change gravity, but also time. In higher dimensions, time could have multiple directions, allowing loops or branching paths. A being within that universe might experience not one flow of time, but many, moving simultaneously along different temporal axes. Gravity would determine how those axes curve, perhaps creating zones where time moves in opposite directions. In such a place, cause and effect could intertwine, and the arrow of time might not point one way, but form a circle. These alien geometries force us to reconsider the word universe. Perhaps our cosmos is not the entire reality, but only a surface within a grander manifold. Gravity, rather than being confined to our world, could be the thread that connects all layers together. The constants we measure, speed of light, Planck's constant, gravitational, strength, might be local properties of our brain, not universal truths. Shift the geometry, and those constants change, birthing a new universe with new laws. Some physicists believe that quantum fluctuations in the bulk could cause brains to collide, releasing enormous energy. Such a collision might look, from within, like a Big Bang. If so, then the birth of our universe could have been the impact between two higher dimensional surfaces, their geometries merging and reshaping. In that instant, gravity as we know it would have crystallized out of the chaos, its strength determined by how the branes curved relative to each other. That process could still be happening elsewhere, spawning new universes endlessly. Even within our own cosmic neighborhood, geometry hints at unseen structure. The curvature of space-time on large scales, the way galaxies cluster and voids expand, could be a shadow of higher dimensional geometry projected into our world. The faint tug of dark energy, driving expansion, might be the effect of curvature leaking in from beyond our dimensions. If so, then our universe is a dynamic surface floating in a vast geometric ocean, its waves felt as gravity, its tides as cosmic expansion. In contemplating these possibilities, one sees that geometry is the true engine of creation. Change its form, and everything else follows. Particles, forces, even consciousness. Gravity is geometry's language, the translation between shape and motion. In alien universes, that language would be rewritten, but the grammar of connection would remain. Space and time, however many dimensions they contain, still find a way to bind energy and structure. Perhaps somewhere in the multiverse, a being made of higher dimensional matter looks toward its own sky and wonders about us, sensing faint ripples of gravity leaking from a neighboring brane. To them, our universe would appear ghost-like, a shimmering four-dimensional film floating in the distance. And perhaps their geometry, their version of space-time, bends in ways we cannot yet imagine, but that follow the same eternal rule. Wherever there is geometry, there will be gravity. Gravity has always been the most mysterious of the fundamental interactions. It is the only force that acts universally on all forms of energy, the only one that shapes both galaxies and grains of dust, and the only one that still resists full unification with quantum theory. Yet a new idea has been slowly emerging in theoretical physics, one that redefines what gravity even is. Perhaps it is not a fundamental force at all, but a phenomenon that arises from something deeper, a side effect of quantum information itself. In this view, gravity does not curve space-time. Rather, space-time curves because of gravity's deeper statistical origin. The notion that gravity might be emergent began as a whisper among physicists seeking to connect the equations of general relativity with the microscopic behavior of quantum systems. The first clues came from black hole thermodynamics. When a black hole forms, it seems to hide information behind its event horizon. Yet, in the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy proportional to the area of that horizon, not its volume. Entropy, in physics, measures the amount of hidden information. The fact that it scales with surface area suggested something extraordinary, that the information content of a region of space depends not on its volume, but on its boundary. This principle, known as the holographic principle, implies that all the information within a volume of space could be encoded on a lower dimensional surface surrounding it, much like a hologram. Gravity, according to this idea, might emerge from the way information is stored and processed at those boundaries. The shape of space-time, in other words, could be a manifestation of how quantum information organizes itself. When that organization changes, the curvature changes, and what we perceive as gravity arises from that reconfiguration. Eric Verlinde, a Dutch theoretical physicist, expanded this idea into what he called the theory of emergent gravity. He proposed that gravity is not a fundamental interaction like electromagnetism, but an entropic effect, a macroscopic result of microscopic information rearranging toward equilibrium. When matter moves, it changes the amount of information encoded in space-time. That change creates a force we interpret as gravitational attraction. Just as pressure and temperature emerge from the collective motion of molecules, rather than any single molecule, gravity could emerge from the collective dynamics of quantum bits of information. If this is true, it means that space-time itself is an emergent structure. It is not the arena in which events happen, but the product of those events, the network of relationships among bits of quantum information. In some universes, that network might be denser, making gravity appear stronger. In others, it might be looser, leading to weaker or more diffuse gravity. The geometry of reality, then, depends on how information connects, how entanglement patterns spread, and how those connections evolve over time. This concept links to the growing field of quantum gravity, where researchers like Juan Maldacena and Leonard Susskind have shown that spacetime geometry can emerge from entanglement. The ADS-CFT correspondence, a mathematical framework connecting a gravity-filled universe to a lower-dimensional quantum system without gravity, supports this view. In that relationship, the gravitational world is dual to a world of pure quantum interactions, suggesting that gravity and spacetime are byproducts of deeper quantum laws. In such a picture, gravity is not something added to the universe. It is the universe's memory of how information flows. When matter gathers, it affects the connectivity of the quantum network, and that distortion manifests as curvature. Time itself could arise from the directionality of information flow, from cause to effect, from low entropy to high. The arrow of time and the pull of gravity may thus share a common origin in the fundamental tendency of the universe to increase its informational entropy. If gravity is emergent, it must also vary across possible universes. In a cosmos where quantum information behaves differently, where entanglement is sparse or chaotic, the emergent geometry might not resemble smooth spacetime at all. It could fragment into regions with independent metrics, where gravity behaves differently from one place to another. Perhaps there are universes where information does not diffuse but oscillates, creating alternating zones of attraction and repulsion. There could even be universes where information remains perfectly ordered, leaving no gradient for entropy to act upon, no gravity, no time, no change. This perspective transforms our understanding of reality. It means that what we perceive as laws of physics might themselves be emergent regularities, stable only within certain informational conditions. Just as the behavior of a gas changes when temperature and pressure vary, the behavior of spacetime could change when the density of information shifts. Gravity would then be as real as sound or temperature, an emergent but tangible property of the underlying microstructure of existence. If one could zoom into the smallest scales of the universe, beyond atoms, beyond quarks, beyond even the Planck length, perhaps one would not find particles or waves, but pure information, bits of reality connected by rules we do not yet understand. These bits might form networks resembling quantum circuits, their connections shaping the geometry of the universe itself. Where connections are dense, curvature forms. Where they are sparse, space stretches. The force of gravity would then be the natural drive of this network to maintain balance, pulling information toward equilibrium. Such an idea aligns with observations that challenge traditional gravity. The accelerated expansion of the universe, for example, might not require dark energy if gravity itself changes on large scales due to informational effects. Valinda's model predicts deviations from Newtonian gravity that could explain the behavior of galaxies without invoking unseen matter. Though still under investigation, these theories suggest that gravity may be flexible, context-dependent, and deeply tied to the flow of information through the cosmos. If gravity emerges from information, then in other universes where the fundamental logic of that information differs, the resulting gravity might not even resemble a force. It could manifest as coherence, attraction, or even synchronization between patterns of energy. A universe might evolve not through motion, but through reconfiguration of its informational structure. What we call spacetime might be one kind of network among many possible kinds, each with its own emergent rules. The implications extend beyond physics into philosophy. If gravity and spacetime are emergent, then so too might consciousness be, a macroscopic phenomenon arising from informational complexity. The same logic that shapes the cosmos could shape the mind. Perhaps both gravity and thought are expressions of how information organizes itself into self-consistent patterns. In that case, the boundary between the physical and the mental dissolves. Both become aspects of a deeper informational reality. Our universe, viewed this way, is not a static arena, but a living computation. Every star, every particle, every quantum fluctuation participates in an ongoing calculation that determines the curvature of space and the passage of time. Gravity is the output of that process, the visible manifestation of invisible logic. Each moment of existence is a frame in that computation, connected to the next by the rules of entanglement. Whether this picture is true remains uncertain. We have not yet unified Einstein's geometry with quantum mechanics, but the emergent view offers a compelling path. It suggests that the universe's structure is not imposed from above, but grows naturally from the simplest principle of all. That information seeks equilibrium. From this principle arises order, curvature, time, and everything we call gravity. If that is indeed the case, then our universe is not just one among many. It is one expression of an infinite number of informational possibilities. In others, the rules may differ, producing gravities of other kinds, some attractive, some repulsive, some beyond comprehension. But all would share a single truth. Wherever information flows, geometry follows. And in that geometry, gravity is born again and again, not as a force, but as the memory of existence itself. From the first falling apple to the curvature of distant galaxies, gravity has been the thread that ties the cosmos together. It shapes not only the paths of planets and the fates of stars, but also the very possibility of meaning within the universe. Without it, there would be no stable worlds, no flow of time, no sequence of cause and effect. Gravity is not simply a background feature of nature, it is the architecture of existence. It defines the rhythm by which the universe unfolds. And yet, as we have seen, gravity may not be universal in the way we imagine. Across the endless landscape of possible universes, its strength, form, and even its essence could differ. In some realms, it may be overwhelming, collapsing everything into black holes before thought can arise. In others, it may be so faint that matter drifts eternally, never gathering, never igniting. There may be universes where gravity repels rather than attracts, or where it flickers, alternating between drawing matter together and pushing it apart. Each possibility reveals how finely balanced our own cosmos truly is, a harmony so precise that even a minute variation would erase the possibility of life. Our gravity, gentle yet persistent, allows the universe to endure. It gathers hydrogen into stars, stars into galaxies, and galaxies into the grand web of cosmic structure that stretches across billions of light years. It is slow, patient, and irresistible. The same force that holds the moon in orbit also guides the expansion of the universe itself. Through gravity, the cosmos remembers its own history. Every cluster of galaxies, every ripple of gravitational waves carries the record of what came before. Einstein showed us that gravity is geometry, that matter tells space how to curve, and space tells matter how to move. But even this elegant description might be incomplete. Modern theories hint that gravity could be emergent, arising from deeper layers of information or quantum entanglement. If so, then the universe's geometry is not fixed, but continuously computed, like a vast equation unfolding in real time. Each moment, each motion, is a solution to that equation. Time itself may be the unfolding of the universe's effort to balance the relationship between energy and curvature. To reflect on this is to glimpse something profound: the connection between gravity and existence itself. Without curvature, there is no motion, and without motion, no time. Without time, there can be no change, no evolution, no thought. Gravity is what allows the universe to move from potential to actuality. It gives direction to causality. It creates the arrow of time by binding matter to geometry, ensuring that every event has both origin and consequence. In this sense, gravity is not just a physical phenomenon, but the framework through which meaning arises. Every story, every process, every act of becoming depends on it. A universe without gravity would be static, frozen in possibility, but devoid of experience. A universe with infinite gravity would be equally still, crushed into singularity. Only in the narrow middle ground, where gravity bends space without breaking it, can complexity exist. Our universe resides precisely in that middle, suspended between chaos and stillness, where curvature allows patterns to form and endure. Consider how gravity weaves the history of the cosmos. It began as a whisper in the early moments after the Big Bang, when the first density fluctuations grew under its pull. Over billions of years, it sculpted those fluctuations into galaxies and stars, then planets and oceans. It guided the paths of meteors, determined the rise of tides, and even shaped the evolution of life by setting the rhythm of the days and seasons. Gravity made time itself measurable, giving the universe both heartbeat and memory. If other universes exist, their gravities would compose other songs. Some would be swift symphonies of collapse, burning bright and dying fast. Others would be long, silent adagios of endless expansion. A few might contain structures unlike anything we can imagine, cosmic webs that pulse or fold, gravity acting not as a constant, but as a living variable. Each of these universes would tell a different story of existence, all written in the language of geometry. Perhaps the greatest mystery of gravity is that it seems to transcend its own scale. It governs everything from the smallest falling pebble to the largest galactic cluster, and yet it unites them within the same principle. That unity hints at something more fundamental, an underlying coherence that pervades the universe. Whether through space-time curvature, information flow, or entropic balance, gravity expresses that coherence as structure. It is the way the universe holds itself together, ensuring that it remains one connected whole rather than dissolving into randomness. There is a quiet poetry to that realization. Gravity is not loud like light or volatile like magnetism. It is subtle, almost shy, but it endures. It reaches across every void, carrying influence even where no other force can act. It is the soft persistence of connection, the unseen hand that keeps the stars from drifting away. In its patience, it embodies something eternal, the universe's own will to remain coherent. If gravity is indeed emergent, then so are we. The atoms that form our bodies were forged in the hearts of stars held together by gravity, and the neurons that allow us to think operate within a geometry defined by it. Our sense of time, of continuity, of belonging to a story larger than ourselves, all are consequences of the curvature we live within. To understand gravity is to understand the conditions that make consciousness possible. It is the link between physics and experience, between the external and the internal universe. One day, humanity may fully understand gravity's origin. We may unify general relativity with quantum theory, decode the holographic fabric of spacetime, or discover how information gives rise to curvature. But even then, the wonder will remain. For gravity, whatever its ultimate nature, will still be the law that binds everything, matter, energy, and meaning, into one coherent whole. And so, as we reflect on the endless possibilities of other universes, we realize that our gravity is neither too strong nor too weak, neither too simple nor too chaotic. It is precisely what it needs to be for the universe to think about itself. Through gravity, existence achieves awareness. It allows the cosmos to not only exist, but to understand that it exists. Perhaps that is gravity's final secret, not just that it bends space and time, but that it bends them into reflection. It turns the universe inward, allowing it to ask questions, to imagine other possibilities, to dream of what could be. In that sense, gravity is not only the force that binds worlds and stars, it is the force that binds thought to being. In another universe, gravity might pull harder. In another, it might not exist at all. But here, it balances perfectly, binding atoms into matter, matter into stars, stars into galaxies, and galaxies into awareness. It holds us to the ground, even as it lets us reach for the sky. Without it, nothing would fall, and nothing would ever rise.